Hello everyone, myself Rupam Das, Assistant Professor of Asansol Engineering College in Electronics and Communication Engineering Department. This is my second lecture. Name of the subject is Signals and System. Learning outcomes are at the end of the session, student will be able to understand various types of signal. Contents are energy and power signal and some basic elementary signals. These are the reference book. First book is Signals and System by Anand Kumar. Second book Signals and System by Tarun Kumar Rawat. Third book Signals and System by Ramesh Babu. And fourth book Signals and System by Nagor Kani. Energy and power signal. First of all, power signal. A signal is called as a power signal if its average normalized power is non-zero and finite. It has been observed that almost all the periodic signals are power signal. Energy signal, a signal having a finite non-zero total normalized energy is called an energy signal. It is observed that almost all the non-periodic signal defined over finite period are energy signal. As these signals are defined over finite period, they are called as time limited signal. Time average DC value of the signal, the time average or DC value of the signal xt over all time is defined as time average or DC value xt is equal to limit t tends to infinity 1 divided by t integration minus t by 2 to t by 2 xt dt. The integration of xt from minus t by 2 to t by 2 gives us the area under xt between the time limits minus t by 2 to t by 2. This area is then divided by t to obtain the average value of xt, and as the limit of t tends to infinity is taken, the average is calculated over the entire time range from minus infinity to plus infinity. Energy, the total normalized energy for a real signal xt is given by m capital E is equal to minus infinity to infinity x squared dt. However, if the signal is complex, then the expression for total normalized energy is given by capital E is equal to minus infinity to infinity xt mod of xt whole square dt. These equations indicate that energy is the area under x square t, the curve over minus infinity to plus infinity, hence it is always positive. This is the comparison between energy and power signal. In case of power signal, the signal having finite non-zero power are called as power signal. Energy signal, the signal having a finite non-zero energy are called as energy signal. Number two, for power signal, almost all the periodic signals in the practice are power signal. Energy signal, almost all the non-periodic signals are energy signal. Number three, power signals can exist over an infinite time. They are not time limited. Energy signals exist over a short period of time. They are time limited. For power signal, number four point is energy of a power signal is infinite. Power for energy signal, power of an energy signal is zero. Now one question is given to you, okay, what is the total energy of the rectangular pulse as shown in the figure? Now for this, according to the formula, energy is given by minus infinity to plus infinity x squared dt, that is equal to minus t by 2 to t by 2 a squared dt. A square, if I am going to solve it, t minus t by 2 to plus t by 2, after solution it is coming energy is equal to a square into t1. Now next, another problem is been given to you. From this particular signal, power and energy is going to be find it out. So according to this problem, power is been defined as p is equal to 1 divided by t integration 0 to t x squared t dt. But here in this case xt is equal to 1 for the limit 0 to t by 2, and this t is equal to -1 for t by 2 to t. So by using this we can apply it in a formula. P is equal to 1 by t 0 to t by 2 1 squared dt plus integration t by 2 to t minus 1 whole square dt. So it is coming 1 by t 1 into t 0 to t by 2 plus 1 t t by 2 to t, and finally after solution it is coming 1. Next is find the energy and power of the following signal. The signal is been given xt is equal to a cos 2 pi f0 t plus theta. So from this we can write power, that is equal to limit t tends to infinity 1 divided by t minus t by 2 to t by 2 a square cos square 2 pi f0 t plus theta into dt, that is equal to limit t tends to infinity 1 by t integration minus t by 2 to t by 2 a square by 2 1 plus cos 2 2 pi f0 t plus theta into dt. Now after solution it is coming again in the next line, limit t tends to infinity a square by 2t minus t by 2 to t by 2 plus limit t tends to infinity a square by 2t minus t by 2 to t by 2 cos 4 pi f0 t plus 2 theta into dt. And after solution again it is coming a square by 2t multiplied by t by 2 plus t by 2 plus 0. So finally power is coming a square by 2. Next, energy of this signal is given by capital E is equal to minus infinity to infinity a square cos square 2 pi f0 t plus theta into dt, that is equal to a square by 2 integration minus theta pi minus infinity to plus infinity 1 plus cos 2 into 2 pi f0 t plus theta into dt. So it is coming a square by 2 minus infinity to infinity dt plus a square by 2 minus infinity to infinity cos 2 2 pi f0 t plus theta into dt, and after solution it is coming capital E is equal to infinity plus 0, so it is coming finally infinity. So this is the final answer for energy. Next, multi-channel and multi-dimensional signal. In case of multi-channel signal, as the name indicates, multi-channel signal are generated by multiple sources or multiple sensors. The resultant signal is the vector sum of signal from all channels. The examples of multi-channel signals are: a common example of multi-channel signal is ECG waveform. To generate ECG waveform, different leads are connected to the body of a patient. In case of multi-dimensional signal, if the signal is a function of signal independent variables, the signal is called one-dimensional signal. On the other hand, if the signal is a function of multi independent variables, then it is called as multi-dimensional signal. A good example of multi-dimensional signal is the picture displayed on the TV screen. To locate a pixel on the TV screen, two coordinates, namely x and y, are required. Next, this is the difference between multi-channel signal and a multi-dimensional signal. First point, such signals are generated by multiple sources or multiple sensors, but for multi-dimensional signal, such signals are function of many independent variables. Number 2, ECG signal, and mathematically it can be represented by xt is equal to x1, x2t and x3t. And for multi-dimensional signal, picture displayed on TV screen, mathematically it can be represented by p bracket under bracket x comma y comma t. Now these are the some basic elementary signal. First point, that is DC signal, then unit step, sinusoidal signal, signum function, rectangular pulse, delta or unit impulse function, exponential signal, and sin C function or sinc function. First of all, DC signal, a continuous time DC signal. A DC signal is as shown in the figure. As seen from the waveform, the amplitude A of a direct current DC signal remains constant independent of time. The DC signal can be represented mathematically as xt is equal to capital A for minus infinity to plus infinity. This is the graphical representation of DC signal. Next, discrete time DC signal. This is the graphical representation, and the signal is extended from minus infinity to plus infinity. This signal can be mathematically represented as follows: xn, that is equal to a under the limit minus infinity less than n less than infinity, or it can be represented in the infinite sequence form as follows: xn is equal to a, and this is the indication where the signal is going to start it. Next, sinusoidal signal. This is the graphical representation of the sinusoidal signal, and this sinusoidal signal can be mathematically represented as xt is equal to a sine omega t, that is equal to a sine 2 pi ft. Next, discrete time sinusoidal signal. Discrete time sinusoidal waveform is denoted by xn is equal to a sine omega n, that is equal to a sine 2 pi fn. Here a is the amplitude and omega is the angular frequency, that is equal to 2 pi f. And this is the waveform of discrete time sinusoidal waveform. Unit step signal. A continuous time unit step signal is the unit step signal is as shown in figure. It is to be constant amplitude of unity for the 0 or positive values of the time t, whereas it has a 0 value for negative values of t. The unit step signal is mathematically represented as unit step signal is equal to ut is equal to 1 for t greater than equal to 0 and for t less than 0, that is equal to 0. And this is the graphical representation of unit step signal. Next, a discrete time unit step signal. A discrete time unit step signal is denoted by un, and the value of unity for all positive values of a small n. This means the value is 1 for n greater than equal to 0, while for other values of n its value is 0. Un is equal to 1 for n greater than equal to 0 and its value is equal to 0 for n less than 0. So un is equal to 1, 1, 1, 1. This signal is graphically represented in the figure as shown in the figure. Next, signum function. The signum function graphical representation is shown in the figure, and it's mathematically it can be represented at signum function of t, that is equal to 1 for t greater than 0, and it is equal to minus 1 for t lesser than 0. The signum function is an odd for antisymmetric function. Next, discrete time signum function. A discrete time signum function can be obtained by sampling of continuous time signum function. It is the train of samples of values plus 1 for positive n and minus 1 for negative n as shown in the figure. The discrete time signum function is defined mathematically as xn is equal to signum function of n is equal to 1 for n greater than equal to 0 and its value is equal to minus 1 for n lesser than 0. This is a rectangular signal, a continuous time rectangular pulse of amplitude a and duration t. The other general type of rectangular pulse having amplitude a over duration t is shown in the figure. The pulse is also centered about t is equal to 0 and it's mathematically represented as a rectangular function of t divided by capital T, that is equal to a for minus t by 2 to t by 2, and its value is 0 elsewhere. In this expression, t shows that it is a function of time and capital T represents the width of the rectangular pulse and a is the amplitude. Rectangular pulse is an even or symmetric function, so hence we can write xt is equal to capital A rectangular function of t divided by t. T is the variable is time t, capital T is the width of the pulse and A is the amplitude. And this is the graphical representation where it is possible to represent rectangular pulse signal in frequency domain as follows. So xf is equal to a rectangular function rect t f divided by 2w, and this is the graphical representation of rectangular pulse. Next, discrete time rectangular pulse. This is a graphical representation. A discrete time rectangular pulse of figure is represented mathematically as xn equal to a rectangular function of n divided by capital N, where a is the amplitude, capital N is the width, and a rect n divided by capital N is equal to a under condition minus n by 2 to plus n by 2 and 0 elsewhere. Delta or unit impulse function is delta t. The delta function is as shown in the figure. It is present only at t is equal to 0. Its width tends to 0 and its amplitude at t is equal to 0 is infinity large, so that the area under the pulse is unity. Due to the unity area, it is called as unity impulse function. Delta function delta t is equal to 0 and the area under unit impulse is given as the area the unit impulse is given as the area under impulse equal to minus infinity to plus infinity delta t dt, that is equal to 1. Next is a unit sample signal delta n. The discrete time version of unit impulse signal is the unit sample signal. A discrete time unit impulse function is denoted by delta n and the amplitude is 1 for n equal to 0, and for all other values of n its amplitude is 0. Delta n is equal to 1 for n equal to 0 and for n not equal to 0. The sequence from it can be represented as 0001, 000, and for delta n is equal to 1 and its graphical representation is shown in the figure. Next is unit ramp signal. The discrete time unit ramp signal is denoted by URN. The value increases linearly with sample number n. Mathematically, it can be represented as URN equal to small n for n greater than 0 and 0 for n less than 0. And this is a graphical representation discrete time unit ramp signal, and it is continuous time ramp signal. The continuous time ramp signal is also denoted by a small rt, and it's mathematically represented as rt is equal to capital T small t for t greater than equal to 0 and its value is 0 for t lesser than 0. Continuous time exponential signal. The continuous time exponential signal or complex exponential signal of the following from xt is equal to c e to the power alpha t. Here c and alpha are the general complex number. Depending on the values of these parameter, the complex exponential can be several different characteristics. If c and alpha both are real, then the corresponding exponential signal is called as real exponential signal. The exponential function also are used extensively in the signal analysis. There are two types of exponential function, rising and decaying exponential function, and it is shown in the figure. So these are the figure for decaying exponential function, and this is a rising exponential function. The decaying exponential function xt is equal to e to the power minus alpha t, and the rising exponential function xt is equal to e to the power alpha t. So we have assumed c is equal to 1 for both the equation as shown above. Next is discrete time exponential signal can be expressed as xn is equal to a to the power n. Here a is the some real constant. For a greater than 1, for case 2, 0 less than a less than 1, case 3 a less than minus 1, and case 4 is minus 1 to a less than 0. So if the condition is a greater than 1, so the rising discrete time exponential function can be obtained. So this is the rising exponential function where xn is equal to written a to the power n. A I have considered here 3 to the power n, and if I'm going to put the value of n, so this type of signal can be obtained. Next is for 0 less than a less than 1. So in this case xn is written a to the power n, so that is 1 divided by 3 to the power n. Again, if I'm going to put down the value of n, so this type of signal representation we can obtain. Next is for a lesser than -1. Here a I have taken -3. So xn is equal to -3 to the power n. If this condition is going to be satisfied, then this type of decaying exponential signal can be obtained. Next is -1. For case number 4, -1 less than a less than 0. Here a is equal to -1 divided by 3. Here xn is equal to a to the power n, that is equal to -1 by 3 to the power n. Now this type of signal representation can be obtained. And next is sinc function. The sinc function or sinc false is mathematically expressed as sinc function sin cx, that is equal to sine function of pi x divided by pi x for x not equal to 0, where x is the independent variable. So we can write sinc function of x is equal to 1 at x is equal to 0, sinc function of x is equal to 0 for x is equal to plus minus 1 plus minus 2 plus minus 3, and this type of shape of the sinc function we can obtain. And these are the summary of the elementary signal which we have discussed here. Delta or unit impulse function is discrete domain continuous domain, unit step is discrete domain continuous domain, unit ramp function discrete domain continuous domain, sinusoidal signal discrete and continuous domain. Next is exponential for a greater than 1, for 0 less than a less than 1, when a less than -1, and when it is -1 less than a less than 0. And these are the references for your future purpose. Up to this I conclude my second lecture, and thank you.